Hi everyone, in today's video we will learn about another technique to generate word vectors, Word2vec. Word2vec is very important and we will see in this video the theory part and in the next one an application using Python. So in this theory video we will go over an introduction about Word2vec, what is the importance of the context in this application, what are the two learning algorithms that we can use in Word2vec, uh, continuous bag of words and Skipgram, and the difference between the use of softmax or negative sampling. We will also go over some interesting building functionalities of Word2vec when you use them inside the packages that are already in Python for us, and the main applications of the Word2vec. You can also check the references at the end of these slides if you need any additional information, or you can just let us know if you have any questions. Introduction. This application, Word2vec, was created by Thomas Mikolov in 2013 at Google. Thomas and his students were able to create a better algorithm to create word vectors instead of just like counting frequencies. They were actually able to create something that generalize and contribute to the context of the word. It's an unsupervised model to create word embeddings. Not only represent words using vectors, but can identify semantic similarities between words. And that's very important because we do not only have a word that can be represented by a vector, but we can also say if those words are similar in any way. For example, here we have 3 dimensions, sky, wings, and engine. And we can see like the aircraft, like a helicopter, drone, and jet are the ones in the sky and engine part. And we can also see like sky and wings, we can see that we have bee, eagle, and goose. So we can definitely see if we map our dimensions and our words inside some dimensions, we can see those type of similarities that we were not able to do it before with word continuous with bag of words and TF-IDF. So Word2vec use all the words in the corpus. What that means? That means that use all the available information to train the model. Of course, if you take it out the stop words, that will not be in your corpus anymore. But usually we try to not take it out a lot because those words can help the algorithm to understand the context of the word. So usually every word is important for Word2vec. And the Word2vec predict nearby words. And it's able to create vectors in a way that the context of the words are captured and not only the frequency of the word. It's not as much important how many times the word occurs in that text, but what are the words nearby them? So to give the context, if the words appear in the same context, they are probably similar. So that's the main idea of the Word2vec. And we can see here that we have one context, the man, his son. And we have the predicted word, like the target word, loves. So we have that phrase in our corpus. The man loves his son. And if we get the word loves, we can see that in this context, we have those other 4 words. And the same thing if we have the contrary. If I give the context to the algorithm, the man, his son, it will try to predict the word in the middle and it gets loves. So the importance of the context, we can see here that we have a word that we already talked about, apple. Apple is a word that can be apple, the company, or apple, the fruit. So in different contexts, they will have different meanings. So that's the importance of the context. If we can see that the word apple appears in the same context as the word pear, we will try to figure out, and we're gonna say that this apple in question, the one that we are talking about, is actually the fruit and not the company. However, if the word apple appears in the same context as Steve Jobs, we will say that this apple is actually the company apple and not the fruit. Learning algorithms. We have two learning algorithms for Word2vec: continuous bag of words and Skipgram. So those two learning algorithms are used to generate vectors in different ways. The first one, continuous bag of words, given a context, it predicts the word that are most likely would occur in that context. And the skipgram, given a word, it predicts the context that most likely would occur when that word is present. So we have here, first, the target word is, the center word is the blue one, cat. So we have first, our window is 0. So we don't have any context. We only have the word cat. So the phrase would be, the cute cat jumps over the lazy dog. But then we have a window of 1. So we can see the cat occurs with cute and jumps. And if we expand the window to 2, we can see the cute cat jumps over. So we have a little bit more of context, and that's why this window number is very important. So it's the number of words that we consider nearby our target word. And right here we have those two learning algorithms framework. So for the continuous bag of words, it will input the context and the output will be the word. So all the words nearby the word that we want to predict will be given, and we're going to predict what is the most likely word that will be in this context. And on the other hand, for a skipgram, we will input a word, and given the output will be the given context that would likely occur. For example, if we give a context that we are talking about Steve Jobs and MacBooks, iPhones, the output word could be Apple. And on the other hand, if we give Apple without any context, and it will highly depend on our corpus to determine what context that word will occur. If it's the fruit, it will give you the context of the fruit occurring. If it is the apple, the company, it will be the output. The output will be the context that that word will most likely occur. First, we will talk about continuous bag of words. Continuous bag of words use the same principle of the bag of words model. The difference is that continuous bag of words try to generate dense vectors instead of sparse vectors. Remember, sparse vectors are the long vectors where most of the values equals to 0. And the dense vectors are shorter vectors where most of the values are not 0. And we can see here like the dense vectors and the sparse vectors. The continuous bag of word also tries to predict the current target word, the center word, based on the context of the surrounding words. So again, we have the context word as the input. We have a hidden layer that will make all the calculations, and we output the target word, the center word, instead of the contrary that happens with skipgram. So this we have one example. The boy walked to the red house. The input would be the context words, the boy to the red house. And what is missing there? The output would be the target word, walked. Another example would be, the life is not easy. The input would be the life, not easy. The output would be is. Skipgram. Consider the reverse of the continuous bag of words. Instead of predicting the target word, predicts the context of that target word. predict the probability of the target word being in a context. It becomes complex if there is many words in the corpus or many words to be predicted. For example, the window size, it's how many words in the context, like I already said. If we have a window size of 3, we're going to consider 3 words before the target word and 3 words after the target word. So the black cat jumped on the table. So the target word is jump and the context word is the black cat on the table. The skipgram part, like this learning algorithm, learns from the number of times each word appears in the context of others. So, like we use always the example of apple. If apple occurs in the context of other fruits in the same context, we will see that this apple is actually the fruit. So we will input the target word, let's say apple, and we're going to output the context words. What are the words that occur with this word? The goal is to predict the word that is most probable given the words as the input. It calculates the probability based on the entirety of the input and the output sequences observed by the neural network. I will not get in too much detail of the mathematics behind those two models. First, because we already saw how bag of words work, and also because Skipgram can be a little bit hard to understand mathematically, and we'll use the application instead of the math part. So, but we will go over of the Skipgram formula just to better understand. Here we have the sequence of the training words and the objective function. And here it's kind of a little bit confusing, but it's important to understand that an n-gram is a continuous grouping of any words. And a skipgram is a generalization of an n-gram, such that we have grouping of words, but they no longer need to be continuous. Softmax or negative sampling. The softmax, we can see here in this example, the two differences that we have here. So usually with skipgram using softmax, we will generate this third matrix here, grad W output. So we will actually calculate each column versus the learning rate, and we will have the result um, as the output. But with the negative sampling, we don't calculate the whole grad W output. We don't calculate all that. We select some of the words. We can say here like a positive sample, negative sample, and 3 different negative samples. We actually choose some of the samples to be like representative of the whole population. So instead of doing everything, we just choose part of it. And we have the output. The softmax can be computational expensive, and that's why negative sampling is an alternative for the Word2vec. And the motivation behind the negative sampling is similar to stochastic gradient descent. Instead of changing all the weights each time that we do the interaction, like the iterations, we do not take into account all the thousands of observations, but instead we do a sampling. We use only K of them and increase the computational efficiency of the whole algorithm, because instead of considering all the samples and calculating each time the whole matrix, we only calculate the portion of it. That's the important thing to consider. We will see that the Word2vec used in Python, the package has the option to change to a softmax approach or a negative sampling approach. Usually it comes with softmax, and that's one thing that you have to take into account. If you have a huge data set, and we usually will not use that large of a data set, that the softmax will actually be like super slow. But we have to take that into consideration if we had a um, very large data set, and we have to use Word2vec. And we have this option of using negative sampling instead of softmax. Now we will talk about a summary of the two learning algorithms so we can take to the heart what is really important. So for continuous bag of words, we predict a target word based on the context that that word would occur. The order of the words, it's not important. So we don't really consider the order that words are appearing in the text, but more the context of their appearance. It's faster to train. So if we want a computational light, uh, continuous bag of words is more advisable. Skipgram, on the other hand, predict the context based on the target word. So if we give the algorithm a target word, it will predict the context that that word would highly occur. And take the order into consideration, because it's considering like not only that word, it's not predicting the word based on the context, but the contrary. So the order of the words are very important. And it's a little bit slower to train, and we can see that especially because it will have to output a little bit more information than the continuous bag of words. Here we have some interesting built-in functionalities of Word2vec, and those are available to you if you use the Python package that has Word2vec as a model. So it's very easy to use, and they are very interesting, and you can use them like as simple as just like calling a function. So we can see here that we will see that in practice, in the practice part in our other video, but I would like to show you some of those built-in functionalities and how they work. So first we have the degree of similarity between two words. So given two words, how similar they are. And remember that because we're asking the similarity between those two words that are in our corpus. I cannot ask the algorithm to give me the similarity between two words that are not present in the corpus that I trained the algorithm. So we always will give a data set, so the algorithm will be training and learning and creating the vectors of the words based on that data set. And the data set can be the comments of Reddit, can be a page like Wikipedia, it can be a large data set containing all the words in the world or something like that. Identified out of the context word, that's an important one, and it's funny that it's able to see which word is out of the context. So we have here breakfast, cereal, dinner, and lunch. And the algorithm is able to output that cereal does not match with the other options. And we can use that for politics and any other topic that you want. If that word does not match like the words that would occur in similar context, for example, breakfast, dinner, and lunch would definitely occur in the same context. And cereal, it's kind of related to breakfast. So if we had to put it breakfast, cereal, pancakes, and mm, bottle. Bottle would be the word that doesn't match. So that's one thing that it's very nice to see that the Word2vec algorithm can output. Similar words, and that's one that I used a lot, and it's very interesting to see what are the most similar words to a word. Here we can have, and also, oh, another thing, you can input the similar words to a specific word, or you can actually use like positive and negative. Like if I do woman plus king and remove the man part of this function, like of this equation, we will have queen as the top one. So that makes sense because women plus king, it's like the royal part. But we take it out the man portion of the king, and then we have queen. So that's very interesting that we can see that similarity even using equations to try to figure out them. But if you don't want to use the equation, you can just model most similar and just give a word. And it will give you the word that it's most similar in this context. If you do not put the top n equal to 1, it will give you just the first one. But if you don't, it will probably output the top 10 or top 5, if depending on how you set up your model in the beginning. So the probability of a text of or a word in the model. So model score, we have the fox jumped over the lazy dog. What is the probability of that whole text to appear in our model? 0.21. And also you can use the same thing to check a word. What is the probability of that word occurring in our text? The main applications of Word2vec are the recommendation systems, and we can definitely see why, because they can check the most similar words and the context of those words that you are looking or you are searching, and they will give you something that is similar to what you are looking for. That they have that for almost everything right now that we use, like Amazon, Spotify, Facebook, Netflix, Google, Instagram, TikTok, everything. So recommendation systems are now a hot topic, and learning how to produce word embeddings is very important. Also, another main application is the text analysis that we can do based on social media comments or survey responses. So what we can do here, it's like a text analysis. If we have the answers of a survey and we actually don't want to go over all of them like ourselves as humans and check it out, oh yeah, this is from they want something faster or they want something easier, and you categorize them by hand, you can actually use Word2vec. And here we have an example. Someone said the design is a bit cluttered and there are a lot of distractions. So they got this from this comment. They got the word last, like uh, the example less clutter, like the category less clutter, faster loading, more items, like I wish there were more products, more items. So, and they can categorize all the social media comments or survey responses. Any text analysis can be done also using Word2vec. Here we have the references for this presentation, and you can check them if you wanted more information about Word2vec. I also recommend you to read the paper that actually explain how they got the Word2vec technique, and it's listed